Hey everybody, this is Dr. B here, coming at you with a shorter form and more focused workflow with respect to the 3D elevation program LiDAR data scrape. So you've probably seen a lot on social media about this particular website, usgs.entwine.io, where the big claim is that there's more than 70 trillion data points for LiDAR data for the US. So diving in, let's take a quick look at this. You can see there are a number of polygons on the map, and each polygon is represented in the table below. So hovering around, you can see that the names have some significance here. They're used as a lookup in the table. And we're after these entwined point tile resources. So this is ultimately it's a stack catalog. So if we switch over to the catalog view, you can see that the catalog is just a collection of links. If we were to follow any of these links, then we would get some metadata about each polygon from that map. And we would have the coordinate reference system. We would also have a polygon showing us that area of interest. And then we'll also get the entwined point tile URL, as you can see as assets in the bottom here. So if we take a look at one of those, so also for New York City here, then it's a even more simplistic view. So there's not a lot in it. It just gives us the pseudo Mercator bounding boxes, a point count, the schema for the data set, and then the SRS for pseudo Mercator projection. And then we're going to use Uber's H3 hexagonal discrete global grid system to create subsets of data. So for each hexagon tile in our area of interest, we are going to create a digital elevation model, and we will name it with the hex cell ID. So switching over to the workflow, let's take a quick look here. If you give it that area of interest name, a working directory, and the H3 level of ID, it will start up a parallel process where it will pass that information to a function. So it'll scrape data from the URL direct. It will create these geotiffs output with the H3 cell ID name. And it will do this in parallel, and it'll leverage DuckDB's ability to parallelize itself independent of Python. So it's actually pretty fast. So we're getting around some of the limitations of PDAL and Pandas, where both are natively single-threaded. We can use DuckDB to get around that. The only caveat is that the 3D elevation program hosting site only allows one connection per session. So you can't run the actual download or the actual scrape in parallel. Those won't succeed, but if you set them up one by one with the threading lock, as we've done here, then they'll succeed, and they'll still be pretty fast because they can't all be working at the same time on the server's end, but they can be with the data that they've downloaded. So if we take a quick look at the EPT to DEM workflow, we can see most importantly this bounding box here is three-dimensional bounding box. So that's the first step of the PDAL pipeline that we're building here. The second step is to filter out data of certain classifications. So in this case, we're keeping the bare earth, the topobathymetric, and the submerged objects. Everything else will be excluded. And we're also going to keep only data points that are less than 10 meters elevation. So you don't see that here, but I'm just going to tell you. And then we're going to filter that so that the data only occupies a hex cell. And we're going to tack on what that hex cell ID is at the high resolution. So we actually have two H3 IDs in here. We have one for the cell, and we have one for the pixels within the cell. So we're going to do this with a hopefully 1 meter output in our resolution. So that's the H15 or the H3 level 15. And then level 7 is going to be the hex cell or the tile. So the way that works is it will check the stat catalog for the existence of that area of interest. If it does exist, it will pass that out. We're also going to give a big bounding box, and we're going to let H3 create all of the hexagon cells for us. It's going to do that in DuckDB. So we have a really intimate relationship between Python, Pandas, and DuckDB in this workflow. And then we have a supersede classifications, which is another DuckDB query, which really will just reduce the data. So for any of those higher level of detail H3 cells, so at the 1 meter level, we're going to find all classifications within each 1 meter level cell. We'll sort those out. So we'll partition basically based on the cell ID at 1 meter. And we will rank the classifications, and we will output only one classification. And this is in descending order. So that one classification will be the max. The reverse order or reverse sorted classification. And moving on, that takes us into QGIS, where you can see here we have a whole scrape. This was for the New York City entwined point tile resource, where for the bounding box, we filled it with the hex cells. And then we've, within each hex cell, downloaded and filtered data. So you can see in some cases we don't have any data because we're either above 10 meters elevation or we don't have those certain classifications that we were after. So what would this look like with just a single cell is this. So if we zoom on in, you can see we got a little bit at the bottom of the cell. We got a lot at the top. And you can see we have excluded things like buildings and vegetation and water. So this is a powerful workflow. And it gives us a performant way to navigate the data, but also to do other things with it. So if all you wanted to do was look at the data, you could just go to the stat catalog and follow those POTRI or cesium links, and you can navigate the data. But if you actually want to do things with the data on a very specific workflow, this is a great way to start. So you can use this as an inspiration, hopefully. And if you have any comments, leave them below. And if you have any questions or you'd like to collaborate with me on a workflow, feel free to reach out. I hope you have as much fun with this data set as I have. And good luck to you. Thanks again for watching.